Last week we started talking about arithmetic circuits. We presented the simple adders, and then we presented the half adders, we presented the full adders. We connected them together to make a multi-bit adders. Then we talked about how we present signed numbers in binary. So we can now represent both positive and negative numbers, which is then how we went and took our adders and made subtractors out of them. And we said this will be the very basic of our arithmetic logic unit in our computer, which is what we will talk about today. Now, this topic of computer design fundamentals has not traditionally been taught in this course well, it has been in the previous few years, but if you look quite a few years back, this is, can you close the door? This topic is fairly new, and the reason why it was introduced is because most of you will continue from here into 2142, embedded system design. And it wasn't always clear where's the link between 214 and the digital circuit design into the embedded system design. In 2142, and you will hear a lot about 2142 in today's lecture, I will keep making references to it. In 2142, essentially you will get a processor, an ARM7 processor, and you will learn how to program it, and then you will learn how to connect peripherals into it, and then some aspects of embedded systems. But it's not always clear how is this related to what we've learned in digital design. Obviously, when you build processors, they're built of digital circuits, but what's inside them? So this lecture here today is to fill in the gap. Now, aside from linking it into 2142, this is just plain interesting stuff. Because when I'm sure all of you have computers at home, you all work on the internet, you always know that 3 gigs is the latest one and 64 bits is the latest word in computers and all that, but what does it mean? What's the difference between 32 bits and 64 bits computers? How do computers work? What's inside the processor? And this is the kind of stuff that I want to give you some appreciation today. Obviously, I want to teach you how to design the latest Intel, what's the latest, Centrino, Pentium, I don't know, i7. The i7, which by the way includes inside it asynchronous circuits, just like your assignment. So you won't go into very complex stuff, but the stuff that we will cover today, the fundamentals, are pretty much the building blocks of any processor out there. So everything started from here, and again, when you will be in 2142, you will always be able to link back, and you know the fundamental, what's the circuitry inside your ARM processor. Obviously, the real circuitry will be more complex, but they're all based on this picture here, on this topic here. Now, before I actually start this lecture, we need to cover some basic terminologies. We'll start with defining what a register is. Now, in previous lectures, previous tutorials, I may have referred to registers as memory elements, and I may have used them every once in a while. In your lab, you had lab 5, which was the shift register. So let's define formally what a register is. Essentially, it's a whole bunch of flip-flops next to each other. We know what flip-flops are. A register, just going to be those flip-flops, one right next to each other. In the simplest case, there's no connection between them. They will all have a common clock signal, so we will all load all the flip-flops together at the same time, which essentially let us store a multi-bit value rather than the 1-bit value that the flip-flop let us have. But then we can take it into the next level, have more complex registers that interact between the different flip-flops. And such an example is what you had in Lab 5, your linear shift-back register, which each flip-flop was connected to the one next to it, and then there was some feedback into it. Counters are good examples of flip-flops. They do, of registers, sorry, they do count in a certain way, but essentially they are just few flip-flops right next to each other with a common clock. And registers in general are pretty much good for storing and manipulating information, as I said, when you want to store multi-bit information. Now in today's lecture we will deal with the simple simple registers, just those flip-flops that have no interaction between them, but they do have some common clocking signals and other reset or clear signals to them. As an example, here's an example of a 4-bit register. So essentially, it's just 4 flip-flops right next to each other. Each one of them has a data line coming into it, but they all have a common clock, and they all have an active low, reset, or clear signal to them. So on every rising edge of the clock, whatever data will be on all the D inputs will be stored in all the flip-flops. If I want to clear the whole value of the register, I just need one clear signal, which is asserted low, so I actually pull it down to 0 in order to clear the whole register. And I can have a special symbol to this register, just a cleaner interface to it. There is a problem with this register though. I mean, it does what it said as we defined it, but usually when we use those registers, and let's say in the context of our computer design studies here, we might want to store a value into a register and then leave it there to remember until the next time we might want to load this value to do something with it, or to store a new value into it. Now, computers and other digital systems usually have some master clocking signal that will keep clocking the entire system at some rate. You know, the latest Intel Pentium Centrino i7 thing is 3 gigs maybe, I don't know. Which is obviously not the rate that we want to store new information into this flip-flop there. But we don't have any way with this register here to tell it, just hold on to the value that you have already without loading a new signal on the next rising edge of the clock. So we need to somehow stop the register from loading new signals every time. We want to give it some control that we say, now I want to store a new value, and then remember this until the next time I want to load a new value. So here's a possible solution to how to fix this problem. Either you're going to play with it or you're not.
Well, how do you zoom?
There's zoom buttons.
Oh, hello.
Yeah. Just whatever you do, don't stop the recording, yeah? And make sure there's always a red dot in the screen, yeah? Okay. Do you want a chair? There you go. You're going to have to come and grab it though. The beautiful thing about a video is that I can take this whole conversation and cut it out of the video, like it's never happened. Obviously, when you put yourself on YouTube, you don't want the whole world to see how much of a fool you make out of yourself. Although it's too late now. Alright. So one way of doing this is to prevent the clock from actually getting into the flip-flop, or essentially adding an enable signal into my clock. If you look at the circuit, and we did talk about enabling circuits before, this side, the output, will just be connected to our regular clock. We're going to have the master clock coming in, and we have to, and we're going to have a load or an enable signal as part of the inputs. When this load is 0, the output here will be 1, and this OR gate there will keep our input to the flip-flop, to the clock, always high, regardless of whatever the real clock is doing. Which is why you can see the cases here. The load is low, then the C input stays high, the flip-flop is not being clocked, and therefore nothing new is getting stored into it. When load goes high, this then goes to low, and then the C input just follows whatever the clock is, and this is the case here, and then we just use the flip-flop as we want it to be. Now this kind of design actually represents a bit of a problem. I mean, it works, and you know, as long as you control your load signal accordingly, you can control your flip-flop when you want to load new values. Otherwise, you disable the clock, and then the flip-flop or the whole register just remembers what it had inside. The problem is that when you start putting logic in your clock path, and this type of circuit is what we call clock gating, then you start introducing different delays in your clock path. Now imagine some flip-flops will have this logic into them, some flip-flops will not have this logic into them. Then you will start introducing what's called a clock skew, where essentially you want all your flip-flops to be clocked at the same time, but once you put some additional delay in the clock path to some of the flip-flops, you start deviating from that master clock time. And to show you why this may present an example, a problem, let me show you an example. Imagine we have two flip-flops connected to each other. One of them is connected to the master clock signal. The other one is some function of this clock signal. Let's suppose this is just some propagation delay there. If there was a delay 0 here, so both these flip-flops get clocked at the same time, then when on the rising edge of the clock, this value will now be stored in this flip-flop, and a new value will come and be stored in the first flip-flop. If there's some propagation delay here in the clock path, then this clock will be applied some time before this clock here. So when this is applied, a new value will go into this flip-flop. This will now have a new value, and when this is clocked, the new value will already propagate into this one here. And this is essentially not the behavior that we want. Remember, especially with state machines, we want the old values to then be used to calculate the new values of some flip-flops, and we don't want the new values to propagate through straight away. So how do we go about solving this problem while still having the ability to actually control whether we want to load new values into the registers? Here's another possible solution, which is a D flip-flop with an enable, but now we're not touching the clock path into the flip-flop. The flip-flop clock signal is connected to the regular clock, and now we introduce this structure here that is essentially a multiplexer. And we choose between whether we want to let a new value D propagate into a flip-flop, or if not, we want to take the old value and then push this as if it was the new value. And in order to see how this works, if enable is 0, so we don't want to load any new values in, then this gate output a 0. This gate here, because of the inverted, this is a 1, is dependent on the old output of the flip-flop. And then when enable is low, on a clock rise, D will just be equal to its old value, and then we're not getting any new values in. And vice versa. If enable is now 1, then this gate here will be 0, and this gate will just follow whatever the input D is, and then we choose that whatever will appear on D will be stored in the flip-flop. So this solves the problem of this clock skew, because we're not introducing any delays in the clock path. All the different registers will be clocked at the same time, but we have the ability to choose whether we really want to load a new value or we don't want to load a new value. Now, just taking this aside for a second, let me tell you about the clocking problems when we design really big hardware system or digital system. Imagine you have some chip. So this is a chip and you have all the different input pins to it. And you have some registers and some logic in it, and you want the whole thing to be clocked at the same time. Now, let's say the clock signal is usually a signal coming from an external oscillator, usually some crystal oscillator outside on your PCB, and we feed it into the clock input of the chip. Now, if you had some registers or flip-flops on this side of the chip, and then some other flip-flops on this side of the chip, then you can clearly see that the ones over here are much closer to our clock signal than the ones over there. Now, as I mentioned before, we really do want all the flip-flops to be clocked at the same time. Now, you might say, well, the size of such a chip is maybe, if we had a lot of money, 1 centimeter by 1 centimeter. And that's a huge chip. And I'm not talking about the packaging, I'm talking about the inside of the chip. If you have a 1 centimeter chip, then you're really rich. And you're saying that's not a long distance. I mean, signals travel in the speed of light to some extent, well, depending on whatever resistance you have in the wires. But usually we just ignore this propagation delay. However, when we talk about the clocking frequency that we are actually clocking our chip and the propagation delays through our logic, these delays do come and become significant, and this slight change between the clocking signal here and the one at the top is actually going to represent us with a problem. What they do these days is, and this is true, this is what they do, they take the clocking signal through what's called a clock tree, and they bring a really thick wire into the middle of the chip. And then from there, they start branching this wire into smaller branches that connect to the different elements. And what they try to do is to make sure that the path between the middle and any of the clocking of the clocked elements in your chip is roughly the same. And they try to make it as identical as they can. It's not always possible, but the more identical the paths are, then obviously the clock skew will be minimized. Now, how do you make your signal propagate faster? I mean, one of the main problems for a signal to propagate through is the resistance in the wire. The thinner the wire is, the more resistance you'll have. So just say, all right, I'll make my internal wires thicker. And in today's technology, it's not a problem passing wires because you have different layers on the chip. So you can have one, and this is what they do, they have a layer dedicated to the clock, layer of metal wires. And you can say, I want my clocking wires to be really, really thick, therefore minimizing the resistance, therefore I will get them propagating faster. But what happens when you make the wires thicker?
More space.
More space, okay. So, well, space is not, it's an issue, but not so much, because then I can add another layer. It's not always, we don't have infinitely many layers. It's not a huge problem.
More heat.
Sorry?
More heat.
Heat? Possibly, although when there's less resistance, then it means less heat, doesn't it? Yeah. Okay. Cost? Yeah, that's right. Capacitance. When you start having layers of wires, then essentially you're creating capacitors in them. The larger, the thicker your wire is, the more capacitance you actually add into the chip. The more capacitance, the more you have to charge and discharge it, the slower your propagation becomes. So although you minimize the resistance, now the capacitance is a problem. So you really have to very delicately design those clock paths to match exactly. Now, these things do become a huge problem, and this is why in the assignment we're working with asynchronous circuits, because in the future you will see more and more asynchronous designs coming into these chips. Already, as I said, Intel do have some asynchronous circuits in their own chips. You don't know about this because you don't care, but this is what happens when you go and become a digital designer in the outside world. Let's get back to what we're talking about here. Haven't shown this slide yet, have I? All right, so I went on a tangent too quickly. I was going to do it after this slide. But this is the way to build a register with the new D flip-flop with enable, where the enable is no longer in the clock path. And then we group all of them together. They all have a clocking signal. I took out the clear signal that I had before. Instead, I now have a load or an enable signal to the whole register. Essentially, what I end up with is a register with, in this case, 4 bits, but I can extend to any number of bits, that has a clock, and I can choose when to load values into it, and I can read from it at any time that I want. When you write a C program, and then you compile it, and then you run it on the computer, do you know what happens? And this is a real question, if anybody knows. Surely some of you know, because I know they told you in comp. Yeah?
The compiler breaks it down until it's in system language.
In system language.
Machine code.
Machine code.
And then puts the data in the registers and does the actual operations on what it constructed. Then it spits the answer back out at you. It comes faster, a couple more levels than you see it on the screen.
Very good. Thank you very much. So we have a compiler. So you write a C program. You pass it through a compiler. The compiler will essentially first of all check if your syntax is correct, if your code makes sense. And then it will compile and convert it into machine code, also known as assembly language. Now this assembly language is not quite yet the machine code that a computer can understand. It's still, you can still think about it as given in commands or instructions, although now those high-level C instructions will be broken into much, much simpler assembly instructions. And I will give you examples of what assembly instructions may be. Those assembly instructions are then passed or read by an assembler. They will take those assembly instructions and will convert them into binary codes that a computer can actually read. Computer can't read English, it can read zeros and ones. And then after the compiler and the assembler stages, we end up with an executable file that ends up as a binary file with a whole lot of zeros and ones. And this is now being fed into the computer, and this executes exactly what the original program in C wanted us to do. Now we can break a simple computer into 2 main parts. We can have the data path and the control unit. The data path is there. That contains the brains of your computer. It takes the data, whatever the data is. It does the processing on it, whether it's a mathematical operation, whether it's a logical operation, whether it's a shifting operation, we'll see. Maybe you need to read something from memory, maybe you have to write something to memory. Anything you can do, that's being done in the data path. Anything related to the data, the processing of your data. This data path is controlled by the control unit. The control unit is the unit in charge of passing the correct data into the data path. So the data path may, let's collapse it down into being an adder. The control unit will be the one in charge getting the 2 numbers and pushing them into this adder or into the data path. or it will send any of the control signals, and we'll see them in 2 seconds, into the data path. The data path will then know what to do and will then choose the operation. Now what I want to do is go through this circuit. Now this circuit is what you have in your hands on one side of the page. You can make notes on it, you can write whatever you want. And the way I will analyze this, so this is a circuit for a data path. The data path is controlled by the control unit. The way I want to analyze it, I want to go through each and every part of these let me just see. Is the other side less blurry than this side? Because this seems a little bit blurry from here. No, just as blurry. Anyway, you get 2 to the price of 1 now. Now when you look at this kind of circuit, you're like, whoa, this is overwhelming, this is too much, I don't know what's going on. But really, if you put your panic mode aside and you look into different components, it actually becomes fairly simple and it all makes sense. And this is what I want to do now, to actually go through each one of them. Come on, there we go. The data path is essentially split into 2 main units. You have the register file at the top, so the bluish rectangular there. And you have the register file, and you have the function unit at the bottom. Let's start with the register file. So registers are, well, memory elements that store some immediate data that our processor may want to use. This is not your memory in the computer. When you say you've got 4 gigs of memory, 8 if you're really cool, 16 if you're rich, then this is not this memory here. The memory that, when we say computer memory, this is the external memory, and you can open your computer, you can pull out the chips, you can expand it, you can see those chips there. They don't sit inside your processor. The register file are registers, not that many of them. In this case here, we have 4 registers, R0 to R3. They are sitting right next to the ALU, the arithmetic unit, logic unit, and the function unit overall. Now, the computer memory, by the way, is implementing a whole different technology. It's a much slower memory than the registers that we have here, and it's much cheaper memory. For this reason, because of space issues and cost issues, in regular computers you won't get a lot of registers in the register file. You might get in the older computer 16 registers, you might get 32 registers, possibly 64, but we're not talking about hundreds of registers. Now there's what we call the word length, or sorry, the word width of a computer. When you hear about a 32-bit computer, this is a word width, the natural word width of your computer. And this is all those buses going on here that are marked with N. This is the size of the data that is going through your computer. This is if for a 32-bit computer, you will have registers that can store 32-bit words. With the newer 64-bit computers, the registers are 64 bits. And respectively, the operations that we will do on them will be of that width. So 64-bit computers can take 64-bit numbers and add them together, for example, or do any other operations. So anywhere that you see N from now on, this will be the word width. This diagram here is a very general description for any length or any width of a computer. You can change it as you wish. So we have the 4 registers here. We might want to read 2 of those registers and do some operation on them. So you can see all of the outputs from the registers are connected to two multiplexers, and they're controlled by what's called the A select and the B select, or the A address and the B address. These are 2 bits buses. They can be one of 4 different addresses, and we use them to select which register, or 2 registers, we want to read from. So maybe I want to read the values or the contents of registers 1 and 2. I will put the binary 1 on the A select, I will put the binary 2 on the B select, and the multiplexer will multiplex the corresponding registers out according to the address there. I might want to write to those registers as well. So in order to write to them, I only usually want to write to one of them. I don't want to write to all of them at the same time. I need to have some way of selecting which register I want to write to. This is the address of this decoder right here, the destination address. I might say I want to write into register R3, and therefore I will put the combination for 3 into the decoder, and this will have the effect of only having 3 high at any one time. But I don't want to write to register 3 every time there's a clock cycle. I want to choose, just like we've seen before, when I want to write to it. So for this, I will end it with the load enable signal. That will be ended with all the possible gates that go into the load signal in the registers. And this will enable our writing into the register. So in order to write to register, I have to do 2 things. I have to choose the address of register I want to write to, and I have to enable the loading into the register by asserting this load enable. Only then the corresponding load signal will go into the register, and the data, hey, what data? This data here, coming from down here and then being fed into all the registers, will be written into the corresponding register. So all the registers essentially see this data at the inputs, but they won't actually absorb it. They won't let it propagate in unless the enable signal is enabled, which is this load signal here, and I'm only going to enable one register at any time. Okay. Any questions so far? All right, that's half of it. Now let's talk about the function unit. The function unit essentially has 2 main blocks in it: the arithmetic logic unit and the shifter. The arithmetic logic unit is a unit that does, well, arithmetic and logic. Arithmetic are operations like addition, subtraction, increment, decrement, and then a couple of others. A logic unit is a unit that does bitwise operation on your operand, so bitwise AND, bitwise OR, bitwise XOR, bitwise invert. The arithmetic logic unit, the ALU, will take 2 inputs, A and B, and for now, let's assume those inputs are exactly what's coming down from our register selected by the A and B registers. We will choose what operation we want to do on them using the G-select 4 bits signal, and then the result will be spit out through this line here. And we will see in the rest of this lecture what types of operations and how we actually control what operation we want the ALU can do for us. The shifter takes some n-bit number, so only 1 input, and we can choose whether to shift it 1 bit to the right or 1 bit to the left. Now in this example here, it will be a very simple shifter that only shifts 1 bit to the right or 1 bit to the left, but you can have more complex shifters that can either do several bit shifting, they can do rotation between the number, but we will talk about it when we get to the part where we design the shifter. And if we choose to use the shifter, we ignore whatever's on A altogether. We only deal with the input line B, coming possibly from the registers selected by the B address. Now we have a multiplexer here that will choose whether we were interested in the output of the arithmetic logic unit or the shifter. So this is multiplexer of the function. Whenever I see this, for some reason, I always remember the artist formerly known as Prince. He doesn't understand do. Let it go. In both cases, though, both the LU and the shifter will do the work. They're both sitting in parallel. They will both have data on M, the data on B. But we select which result we want using this multiplexer there. So this is another control signal that will let us choose this. Now, before I said that those registers up there are not our external memory. Our external memory might be a box sitting outside the chip, possibly sitting, whoops. It says mem for memory. Another option that we might want to have is to load up a value from our memory and store it into one of our registers. And in 2142 you will see when we use this option there. Then we have a data in signal that will be connected to the memory. We will ask for a particular data from the memory. This will come through the data in. And then we can select, using the multiplexer of the data, whether we're actually interested in storing the result from the function unit, or maybe we're ignoring altogether the function unit and getting some data coming from externally, from the memory, and storing this back into our register file. So you might have a clock cycle where you don't utilize your function unit at all. It's there, it's combinational circuit, it will be alive, but you ignore whatever comes out from it, and you just take a word from the memory, and when I say a word, I mean a value, and store it into one of our registers. The last thing is this multiplexer here that let us choose what value we want for the variable B. The variable B either being fed into the ALU or into the shifter. We can either choose to have a value coming from the registers, or you might want to set B to be some constant. And this will be good if I want to say I want to add register R2 plus 100, the constant 100. Well, in that case, I can choose the corresponding registers on A. I can put the constant 100 through the constant in line coming from here. And then the multiplexer will choose that I want the constant rather than to read from another register there. Now both lines A and B are also disconnected to the external memory. A will be marked as my address outline. B will be marked as my data outline. This is used if I want to write something to my memory. I will have to choose a particular address in the external memory that I want to write to. So I'll put that address on bus A. The data that I want to write into this address will be put on bus B. And then the control unit will signal the memory to take those address out and data out and push this into the corresponding place in the memory. Now the reason why both the address out and data out are actually connected to my A and B lines is because usually I will have the address that I want to store to in the memory already being in one of my registers there. So I will just load it on the A bus. As for the B bus, for what I want to write into memory, I can either choose to write a constant if I bring this from here, or I can choose to write a value that I had in the register. So I'm just sort of showing you the different options that you can sort of mix and match those control signals to get the different operations. Obviously, you don't have to remember this whole thing by heart. I hope you now have a better understanding of how this whole thing works. So if I showed you the diagram, you will be able to understand what's going on. Oh yeah, something I forgot. From the ALU, we have those status flags coming out, the same status flags that we talked about on Friday. And the circuitry that drives them is exactly the same circuitry that we spoke about at the end of the Friday lecture. So this will give you some information whether the operation in your ALU, if it's negative, if it's zero, whether there's been an overflow, and so on. Now, first of all, any questions? Yes?
Questions on why the negative and zero flag is outside the ALU?
The reason for this is because to determine whether a result is negative or zero, it's enough to look at the sum or at the result coming out. So you see they're connected to the line coming out, because the negative is essentially the most significant bit of the sum. Zero is if they're all zeros. You don't actually need to know what happened here. But for the C and the V flag, these are direct outputs from the actual operation there. It's the carry, and V is the carry in and the carry out of the most significant bit. So that's why they're designed like this. I do want to give you some examples. I'll give you some examples, then we'll take a break. All right? Break's coming. Some of the assembly examples or assembly instructions that you will see in 2142. And I'll show you how they're actually being run here. For example, an assembly instruction will be add R0, R1, R2. This instruction there, what it says is take the numbers inside the registers R1 and in R2, add them together, and store the result in R0. So the way to execute this in the data path, we will choose R1 and R2 using our A and B select lines. So this will be 1, this will be 2. You can see it. We will get R1 and R2 propagating down into our ALU. Obviously in the multiplexer here, we'll choose that we want to use for the B, the register R2. The G select there operation we'll choose will be an add operation. This will be calculated, propagate through. We will choose to take the result from the arithmetic logic unit. And then this will propagate, this is the result from them, will propagate and be written into R0. And we will select I0 by selecting the corresponding destination address. Now, asserting all these signals that I was talking about, the A select, the B select, destination address, the multiplexers, these are all the job of the control unit. The control unit will look at this instruction that you want to execute. It will set the right input signals into this data path, and the data path will therefore pretty much execute what you need to do. Another example of an instruction you will see in 2142, move R3 42. Move, unlike its name, is more like a copy. And it says take the value, the constant 42, and copy it into register R3. In order to do that, I will choose the constant in through the line B. In this case, I will actually select the shifter with no shifting at all, which is one of the things I can actually choose the shifter to just let the signal propagate through. I will then let this signal propagate through, and I will store it into register R3 using the destination address 3. So that's another way of manipulating this, this data path to do exactly what we want there. On the same token, I could have just copied another register, say R2, into R3 by choosing, instead of a constant, choosing another register. Another example. str, a store instruction. It will take the value stored in R1 and will store it in the external memory to the address given in R0. Now this is where some people get a bit confused. In R0, we will have some value already stored in a register, and this value will correspond to an external memory address. So it's a number, but this number will be an address. It will select the corresponding address here, and will send in the data out whatever's in register R1. Essentially, taking the value from R1 and storing it somewhere in the external memory in address given by R0. The last example that I want to give you is a CMP, a compare instruction. And what it says here, compare R1 to R2. Now this is very vague. Handouts, handouts, handouts. What does it mean to compare two numbers? First of all, how do we compare in a computer? And what am I comparing? What should be the result of this thing? Should the result be this number is greater than this one, but possibly equal, and it's also negative in relation to this one? What are the results that we're actually after? 1. Yeah. So the result might be 1. What does that mean?
It's exactly set.
So you weren't kidding? Huh?
And other values if they are not exactly shared.
Okay, so we're comparing whether they're the same or not the same. Okay, that's one way of comparing two numbers. Yeah?
This R1 minus R2 is 0.
Yeah. So this is exactly what a CMP instruction actually does. It takes R1 minus R2, but it doesn't actually store the result anywhere. All it does is to update our status flags. So R1 minus R2, update the flags, and then discard the result altogether. We don't care about what the actual result is. But now by looking at the flags, we can know a whole lot about the relationship between the two numbers. If, for example, the n flag is 1, so it's a negative, we know that R1 was greater than R2. Sorry, so the R2 was greater than R1, because R1 minus R2 resulted in a negative number. Vice versa, if n is positive, then we know that R1 is the greater of the two. If the Z flag is on, so the result is 0, we know that they're identical to each other. Because the only time that you get one number minus the other equals 0 is when both of them are the same. And then some other information we can read from the status flags. We'll leave that to 2142 and how we actually use this and how do we read the status flags and what do we do with them. For now, let's take a break and we'll continue after this.